The idea of combining a differential equation with some kind of point that it goes through is incredibly common in modeling applications, and so we actually give it a name. It would be an initial value problem, and here, we'll talk about this a bit more later, but this is a first order because there's one derivative involved. But an initial value problem is going to be a combination of a differential equation, of course, together with some point in the domain that we can use, and we call that the initial condition. So initial condition plus differential equation is equal to what we often call an IVP, or an initial value problem up here. What we're then looking for is a solution. So there we're looking for a function y that satisfies the initial condition and the differential equation. So let's just work through an exercise of exactly that type. We have the differential equation here, and we have the initial value, or the initial condition, and that partnership together leads to an initial value problem, which will have a particular solution, because we have to not just satisfy the differential equation, it also has to be the single solution that goes through that point. In this case here, the differential equation is fortunately very simple. We note again that the variable in question is t, and t is the independent variable, so we can simply integrate both sides. And when we integrate both sides, careful with it's with respect to t, when we integrate both sides, the dy dt will simply become a y, and then we just have to focus on the integral of the right-hand side as the complicated part. When we do that, we can do our classic add a power here. This is just a polynomial. We'll end up with 2t squared over 2 plus the integral of 1 with respect to t is t, and plus a constant at the end. That would be our general solution, because we could pick any value we liked for c. But if we follow up then as the next step and ask which solution out of this family will also satisfy the initial condition, we would sub in our t equals 0. Notice it's a time derivative, so t equals 0 and y equals 3 as our 2 values that we know. We plug that into our general solution, and we would solve for c. And when we do that, we get 3. I guess we could simplify this a bit further, cancel the 2's. We would have 0 squared plus 0 plus c, and that gives us c equals 3. So y equals, the general solution was t squared plus t plus the constant, but we just found the constant for this particular initial condition was 3, is the solution. So y equals a function of time is a solution. It's a particular solution. And more specifically, that is the particular solution to the initial value problem, short form to IVP, the initial value problem, which is that combination of the equation, differential equation, and the initial condition. Now, we don't always get off so lucky with our integrals, and in this example, we're going to have to look back at some other techniques of integration, but exactly the same idea. Because the variable in question on the right-hand side is just x's, we can simply integrate both sides, this time with respect to x, and that'll give us y on the left-hand side, and the right-hand side will be the integral of x squared times e to the x. We do have an initial condition, but that's something that we apply after we found our general solution. Looking at this integral, it is a classic integral that would cave to an approach of integrating by parts, because we can just keep differentiating away the x squared and integrating the e to the x. So quick reminder, this is the u dv process. We let x squared be our u, our dv is e to the x dx. We integrate both sides of this, we differentiate both sides of this, and we get du equals 2x dx, and our v is the integral of e to the x, that's e to the x. And notice we don't do the plus c yet here, we do that at the very end. We'll have 1 plus c for the whole step. Then we do a quick multiplication here. This integral can be replaced by uv, or x squared e to the x, minus the integral of e to the x times 2x dx. And we'll tidy that up a little bit. X squared e to the x, bring the 2 out front, and then we just have the integral of the x e to the x portion. And then we just do by parts again. This time we'll pick the u to be the x part, and the dv again will be the e to the x part, dx. Integrate both of these, differentiate the u part, and we get du is simply 1 dx's, and the v again is e to the x with no dx. Do our cross multiplication, and this part comes along for the ride. It was there before, we keep it. The 2 comes along. The integration by parts is simply replacing the x e to the x portion. So put all of that in brackets. The x e to the x is replaced by uv x e to the x minus the integral of e to the x dx. All of that multiplied by the 2 out front. With that, we finally have an integral that we can evaluate by inspection, and we end up with y equals x squared e to the x minus 2 x e to the x, and it's negative 2 times negative that, so it'll end up being plus 2 e to the x. And this last integral, at the end of it, we can add our constant for the constant of integration. And that would be our general solution. Of course, this is an initial value problem, so we don't want the general solution. We're being asked for something more particular or more specific. We need to sub in the 0 value for x and the y value for 2 and solve for c. We'll do that on the next page. The x and y values are given here, so we can simply sub those in. Our y is 2, our x is 0, so we'll put zeros throughout here. 0 squared e to the 0, 0, and 0. We'll fill in the blanks in a second. That was 0 squared times e to the 0 minus 2 times 0 times e to the 0 plus 2 e to the 0 plus c. So this whole equation with the x coordinate filled in, and we see so many terms go to 0, it's very convenient for us. Leaving only, careful with the e to the 0 is 1, and we actually have a 2 here and a 2 here. In fact, this gives us at the end of the day that c would be 0. So we actually have a fairly simple expression here. We don't see the c when we're done. We'll have y equals x squared e to the x minus 2x e to the x plus 2 e to the x is the particular solution that we were looking for to this initial value problem. Or what we've been calling an IVP for short.